Today we're looking at the picture of similar triangles and indirect measure. Let's start by talking about similar triangles. Now, similar triangles, of course, is not a new idea. We just want to make sure we're understanding all the concepts and throw in one more just to make sure we can apply all the principles of triangles. Last time, as we talked about similar triangles, we also talked about the idea of corresponding triangles or corresponding parts. To the degree that if I told you that these two triangles were similar, that would mean that they have basically a ratio of the same size. What does that mean? That means the lengths of the sides are going to have a proportional relationship, but our angles are going to stay the same. So we would say that angle Y is the same as angle A. Just like angle X is the same as or congruent to angle B. And of course, then you would say that angle C and Z are also congruent. Because even though the lengths have changed, the angles have not. That's what makes them similar. Same shape. Right? So that idea is review. But today what we want to talk about is our new star idea. And it's a star idea because there's a star shape there. Today we want to talk about the fact that the lengths of corresponding sides, so the same sides, right? The sides that correspond. So in this case, we see how this side, the BC side, corresponds, or is the similar side to XC. So what it says here is the lengths of corresponding sides of similar tragnals. Yeah, tragnals. Here's a wonderful display of superb spelling on my part. Let's make that triangles, not tragnals. Similar triangles are proportional. All right, well, what does that mean? They're proportional. It means that there's a relationship between these two sides. So this side here has a relationship to this side in a proportional way. And a proportions basically just means two fractions that are going to be equal to each other. So let's go ahead and apply this principle with some actual numbers. First of all, we can look at our two similar triangles. We have a 3 by 5, and we're not given the last length, but that isn't significant at this moment. And we're given a unknown by a 10. But now we can start to set things up because we know they are proportionate. Because they're proportionate, first of all, I just want you to do this. What would be your guess for the length of A? Just as you kind of look at the numbers, try and mentally come up with a number. All right, hopefully you've written a number down. If not, well, write a number down. Now we want to prove whether your number is correct or incorrect and why it is. What we're going to do is we're going to make a comparison. We're going to make a proportion. We know this triangle is 3 over 5. This side here compared to this side here. Now, to set up the proportion correctly, we need to make sure that our proportionate sides are on the same part of a fraction. So our 5 here is this side of the triangle, and it's our denominator. So we need this side of our triangle to be the denominator also, which happens to be 10. And because we're solving for A, this side corresponds with this side, and so this is where our A is going to be. From here, we can do one of two different things. If we see a relationship across like this, either direction, we can use that factor to help us solve. Or we're going to cross multiply and divide. Let's do both. Why not? 3 times 10 is 30 divided by 5 gives me an answer of 6. So A equals 6. Or I could have noticed that 5 and 10 have a factorial relationship of 2, so 5 times 2 equals 10. So then I could take in 3 times 2 to get 6 also. So two different ways to work with that proportion depending on what the numbers are. Now, this idea of proportional measurements allows us to do what's called indirect measuring. You know, if I were to ask you to go and find the height of a large tree. Now, most likely you don't have the means to scale up a tree with a long enough tape measure to actually measure that tree. So how could we get what's called an indirect measurement, a very good estimate? And it's going to have everything to do with similar triangles and the proportional relationships that exist. For instance, let's say we want to know the height of this tree. What could it be? What we do know and what we can measure is we know our own height. And for this exercise, we're going to say that this man is 2 meters high, so about 6 feet. So he's 2 meters high, so how high is the tree? Well, at this point, we don't have enough information. Right? However, what we do know is that the sun shines down, that's what the dotted line represents, the light ray, and it shines down at a specific angle at a certain time of day. And if I were to look at that and I would look down, I would notice that the tree has a shadow, and I have a shadow also, or at least this man has a shadow. I don't know if I have a shadow. It's kind of like Peter Pan. Let's stay on topic, stay on topic. Okay, so this man has a shadow. So what we can do is we can measure the lengths of those shadows. So let's say this man has a length of, let's say an 8-meter shadow. All right. So a little bit, it's long. It's late in the day. I guess it's late in the day. Now the tree has, from here to here, has a length of 24 meters shadow. And that's something you could actually measure, right? You're on the ground. You don't have to climb up the tree to measure the length of the shadow. It's right there. It's on the ground, so I can measure that length. So by finding the measure of that shadow and finding the measure of my own shadow, I'm now able to come up with two triangles, right? My first triangle is my tree. It's the height of the tree by my shadow of the tree. So the height, which I don't know, big question mark, here's my sunlight coming down, and 24. Compared to my next triangle, which is the man, who is 2 meters tall, and whose shadow is 8 meters. Because that angle is the same from the light of the sun, and that means your shadow is going to cast the same angular distance, we're going to have two similar triangles. Because we have two similar triangles, now we have a proportion that we can use to solve. So I can take my first triangle, 2 over 8, is going to be equal to my unknown height over my shadow length, right? Here's my shadow, here's the tree's shadow. Same idea, same spot in my proportions, height to height. And now, of course, I can solve this. Now I could reduce if I wanted to. Could make it easier, could make it not, right? I can look for this relationship, and if you're looking for that relationship, you're going to notice multiply by 3. And so multiplying by 3 would do just that. Or, right, you're going to cross multiply and divide. Now, since we see that relationship, let's use that relationship. 8 times 3, of course, is 24. So 8 meters times 3 gives us 24 meters. So 3 times our 2 meters is going to give us, once again, an answer of 6. I must be in love with answers of 6 today. But what that tells us is that our tree is 6 meters tall, which of course is about 18 feet. Right? So it's not an old tree, but I don't think any of us can reach up and touch an 18-foot tree. If you have that ability, hey, you're awesome. Way to go. Let's apply these concepts together now, right? The idea of indirect measurement and the use of proportional uses with triangles as you solve this problem. Here's your sample. To indirectly measure the height of a telephone pole on the playground, some students measured the length of the shadow cast by the pole, as depicted by this picture. How tall was the telephone pole? So they're comparing the telephone pole with a shadow of 24 feet to a meter stick with a shadow of 40 centimeters. Go. That's it for lesson 97. We'll take your questions in class.